Today we're going to talk about a very complicated word, stoichiometry. Stoichiometry, as you'll see in a minute, is going from a known amount of either reactant or product in a chemical reaction to an unknown amount, and how to do that. I'm sorry that this picture is out of focus, but the central idea here, and the thing that I will be hammering home all along, is that the mole, which we talked about last week, is absolutely critical to doing calculations in stoichiometry. And so if you don't understand week 4, it's going to be very difficult for you to do well on week 5. So if there are any questions left on week 4, make sure that you contact me or have extra sessions with your parents or a tutor to try to get a full understanding of formula mass and how to calculate moles and the relationship between moles and mass and moles and particles. Before we do that, I want to make sure that we review the chemical equation. Just like the chemical naming, the chemical equation is one of those concepts that is so important that you should review it 2 or 3 times before you move on. And you'll recall that a chemical equation is a symbolic representation of a chemical reaction. And so this is the sort of chemical equation that we will be dealing with throughout the remainder of this lecture. On one side, on the left side, you have what's called the reactants. In this case, CH4, which is called methane. Now, you would not be given that to name because you don't know how to name that, although you could say that it's carbon hydride because it's a binary compound containing hydrogen. Or you could say that it's carbon tetrahydrogen or tetrahydride, since it's two nonpolar or two non-metal reactants, and there are other compounds that have carbon and hydrogen that have different numbers of carbon and hydrogen. So you could do that, but in general it's called methane, and you've heard of methane. Reacts with oxygen to form, and remember, oxygen is one of those diatomic molecules that I spoke about in class last week. It was one of those things that always, when it's by itself, it travels in pairs. It goes to produce carbon dioxide and water. On the left side are the reactants. On the right side are the products. Below the symbolic representation with letters and numbers is a sort of styrofoam ball, if you will, representation where the red balls represent oxygen, the black balls represent carbon, and the white balls represent hydrogen. And you can see that what occurs here is that a black ball with 4 white balls combines with 2 red ball pairs to form 1 black ball with 2 red balls and 2 red ball with 2 white balls. And you'll notice that there are 4 white balls on one side, 4 white balls on the other side, so it's a balanced equation. 4 red balls on one side, 4 red balls on the other side, and 1 black ball on each side. So the reactants are the substances that undergo the reaction. They're the left side of the arrow. The products are the substances on the right side of the equation, are produced by the reaction, and they're on the right side of the arrow. And the coefficients are the numbers that represent the relative number of reactant molecules and product molecules. Now, as it turns out, what we're getting to today is the fact that these coefficient numbers also will tell us the number of moles of reactant molecules and product molecules. So in this case, you have 1 molecule of methane reacts with 2 molecules of oxygen to produce 1 molecule of carbon dioxide and 2 molecules of water. But you can also say that the 1 mole of methane reacts with 2 moles of oxygen to form 1 mole of carbon dioxide and 2 moles of water. And the relationship between the ratio between the number of oxygen, or the amount of oxygen, or the moles of oxygen, and the moles of carbon dioxide is called the stoichiometric ratio. In that case, it's 2 to 1. And the ratio between the moles of methane and the moles of water is 1 to 2, and that's also called the stoichiometric ratio. And this is absolutely critical in making computations using chemical reactions. So in the same reaction, here you have 3 methane molecules interacting with 6 oxygen molecules to form 3 carbon dioxide molecules and 6 molecules of water. Not only are these balanced, but the ratio that I spoke about before, the stoichiometric ratio, remember I said there was 1 mole of methane for every 2 moles of water. That's stoichiometric ratio. So 3 is to 6 as 1 is to 2. And so this ratio helps you understand exactly how much in terms of molecules or moles you need and how much you will produce. So this is a balanced equation. This is an equation where the atoms are the same on both sides, and this balancing tells you what the stoichiometric ratio is. So for example, this, if you were going to balance this by inspection, you see that you have 1p on one side and 4 p's on the other, so you'll need a coefficient of 4 in front of the p on the reactant side, on the left side. And you also see that you have 10 oxygen molecules on the left, or on the right, and 2 on the left, so you need a 5 beside the oxygen. But this also tells you the stoichiometric ratio between P and P4O10 is 4 to 1, and O to P4O10 is 5 to 1, so that it takes 5 molecules of oxygen to make 1 molecule of tetraphosphorus decaoctane, oxygen oxide, and it takes 4 molecules of phosphorus to make 1 molecule of tetraphosphorus decoxide. It also tells you that it takes 4 moles of phosphorus to make, and 5 moles of oxygen to make 1 mole of tetraphosphorus decoxide. If you balance this, you know that you have a 1, which you don't have to write in front of the barium chloride, a 1 again, which you don't have to write in front of the sulfuric acid, yet again another 1 in front of the barium sulfate, and a 2 in front of the hydrochloric acid. And this tells you that the stoichiometric ratio is 1 to 1 on the reactant side and 1 to 2 on the product side. So it takes 1 molecule of barium chloride and 1 molecule of sulfuric acid to produce 1 molecule of barium sulfate and 2 molecules of hydrochloric acid, or 1 mole of barium chloride plus 1 mole of sulfuric acid to form 1 mole of barium sulfate and 2 moles of hydrochloric acid. If you were to balance this, you would know that you'd put a 3 in front of the hydrogen and a 2 in front of the ammonia. So your stoichiometric ratio is 3 to 1 to 2. 3 molecules of hydrogen, 1 molecule of ammonia or nitrogen to form 2 molecules of ammonia, or 3 moles of hydrogen, 1 mole of nitrogen to form 2 moles of ammonia. And again, you see that in this diagram we've already seen 3 of those diatomic molecules I mentioned last week: oxygen in the first equation, hydrogen and nitrogen in this equation. Now this one's a little more complex, but let's see if we can do it. You know that you're going to need a 2 in front of the carbon dioxide, and you're going to need a 3 in front of the water. However, when you do that, you end up with 7 oxygens, which is 3.5 on the reactant side. Well, when you get a half, you multiply everything by 2. So you end up with 2 in front of the ethane, which is C2H6. A 7 in front of the oxygen, a 4 in front of the carbon dioxide, and a 6 in front of the water. So that tells you it takes 2 molecules of methane plus 7 molecules of oxygen to form 4 molecules of carbon dioxide and 6 molecules of water. And you can substitute for molecule, again, the word mole. Now, reactions, when they occur, can produce various types of products. And in addition to the classifications that we've talked about before, including single replacement, double replacement, decomposition, composition, and oxidation reduction, you can also talk about the precipitation reaction. The precipitation reaction is when one or more products becomes a solid. Now, the concept of solubility is important to understand when you think in terms of a precipitation occurring. Now, in the case on the left here, what you have is this yellow material coming out in solution and sinking to the bottom. And that yellow material is called a precipitate. It's relatively insoluble in the liquid that's in the beaker here. And solubility represents the maximum amount of a substance that can be dissolved in another substance, or the maximum concentration of a substance that can be achieved in the circumstances that the substance finds itself in. If something is soluble, then that means that the substances will dissolve, and usually will dissolve a fairly large amount, whereas if it exceeds its solubility, a precipitate forms. If, on the other hand, it's insoluble, it means that the material is a relatively small amount of material can enter into the solution, and when you see insolubility is when a precipitate will frequently occur at room temperature. Now let's look for a second at what reaction stoichiometry means. Stoichiometry is the process to relate a balanced equation. Remember, in all my discussion up to this point, I've talked about a balanced equation. And it relates a balanced equation to the real, that should be world, calculations in chemistry. And this works very much like a recipe in cooking. What is required and what is produced. When you say what is required, it's not just the name of the things required, but how much. So for example, if you're baking bread, you need not just flour, but a certain amount of flour. You need not just yeast, but a certain amount of yeast. You need not just whatever else you happen to put in your bread, say sugar or what have you. And you need each of those things have to be in required amounts. And then you produce a certain amount of bread. You don't just produce an unending chain of bread. You might produce 1 loaf or 6 loaves, depending on how much flour, how much yeast, how much water, how much of each of the product or reactants you put in there. It's exactly the same with stoichiometry. In this case, you have 2 molecules of aluminum combining with 3 molecules of iodine, another diatomic molecule, by the way, to form 2 molecules of aluminum iodide. Now, nobody can measure a molecule. You can't measure out 2 molecules and 3 molecules. So you remember from last week, a mole is a specific number of molecules. It's 6.02 times 10 to the 23rd molecules. So you can say 2 moles because you know that that represents 2 times 6.02 times 10 to the 23rd molecules, combines with 3 moles of iodine to form 2 moles of aluminum iodide. And you also know that if the formula mass of any compound or any element is the weight, is the molar mass for that compound. So for example, aluminum, if you look it up, is 26.99. That's the formula mass for aluminum in AMU. It's also the molecular mass, or the molar mass, meaning that 26.99 grams of aluminum is 1 mole of aluminum. And that's something you can measure, which is what is critical here. So each of these, if you add up 2 times the formula weight of iodine for iodine's molar mass in grams, And aluminum iodide would be 1 times 26.99 and then 3 times whatever iodine is. So if we were to ask the question, how many moles of iodine are required to react with this kind of weird number, 0.429 moles of aluminum, well, how would we do that? Remember I talked about the stoichiometric ratio. You look at the moles of aluminum, use the stoichiometric factor, and it produces the moles of iodine. So the stoichiometric factor is that there are 3 moles of iodine for every 2 moles of aluminum. So the stoichiometric factor is 3/2. So you take the 0.429 moles of aluminum times 3/2, and it gives you 0.644 moles of iodine.